All right, let's continue on, shall we? So we finished up, and by the way, I've changed document cameras. I think this one's a little bit better. I don't know. We'll see. We finished up last time talking about units of force. We did a quick, very simple example. We'll do more examples throughout the semester, and they'll be more intense than that, obviously. Okay. So, I've got some terms in here from chapter one of we're using the Changle and Bowles text, engineering thermodynamics. I always just kind of say, if time allows, there's some additional slides. I'll try to, for those of you that out there that aren't in my class, I'll try to, at the end of one of these videos, just go through and point to those slides so you can pause the video and get notes if you would like. But normally this is one of those things that I point to my class and say, okay, well, you guys can read, and there's some definitions in chapter one that you need to read and be familiar with. We're going to use throughout the semester. That's really a lot of chapter one. Is a lot of there's a lot of definitions, but there are some things that we need to be really familiar with, and that's normally what I try to pick out first. So what are the things that we really need to be familiar with? What are the most critical ones? And then again, there's some additional terms that I just kind of put at the end. And if I have time in the first couple of lectures, we get to them. If not, I say, hey, they're in my slides. Go learn about these things. Now, but there are some terms that we really need to make sure we're very comfortable with. I'm going to see if I can move this up and out of the way. There we go. Yeah, so system is a term that we will use regularly. And when you see things that are in a quotation, those are direct quotes from your text. Those are, I guess you guys could see. Not, didn't really plan on being on camera, but it's fine. When you see direct quotes like that, these are hi. Let me pause. Okay. So my wife needed my signature, just so you know, she wasn't there and just disappeared. She came and was looking over my shoulder because she needed me to sign something, and now she's gone. So now we can continue. I apologize. I leave this stuff in here so you know I'm human. System, quantity of matter, region in space chosen for study. Vague definition. I always like to say sufficiently vague to be useless. But I was mentioning there, notice the quotes. The quotes means that is a direct quotation from your text. If it's another source, I will give you some documentation on what that source is. But if there's no source provided, that is a direct quotation from the textbook we're using. That is Changle and Bowles, currently in the 10th edition. This is a fair definition, but I don't really love it. Here's one that I like a little better. This is basically, let me pull my pen up. Anything, anything we can isolate from the surroundings. When I was taking thermo, they told us, think about a system as anything you can draw a dotted line around, right? Anything that I can draw a dotted line around and isolate from the surroundings with that dotted line, that serves as a system, which is literally anything, right? Because that dotted line is imaginary. That's so it could be a real that dotted line could represent a real surface. It could represent an imaginary surface. It doesn't have to be actual real, but anything that we can isolate from the surroundings. And that's basically what the definition is saying, is a quantity or region space that we've isolated from its surroundings so we can study. It can be massive, it can be very small, a single atom, possibly even a quark if you really want. Anything that we can, again, isolate from the surroundings is a system. And the best way we can isolate it is just simply draw a dotted line around it, as I drew earlier. So the surroundings are everything that's not in the system, and the the dotted line, the boundary, is what we use to separate from the system from its surroundings. So that boundary, it can be real, it can be imaginary. Um, The boundary can be real, it can be imaginary, it can be moving. We're going to see problems a little bit later in the course where we're going to be dealing with a moving boundary, an expanding or compressing boundary where the system is changing volume. So we'll see that starting in chapter 2 briefly and then heavily in chapter 4 and beyond. But the boundary has no thickness. What that means basically is it's kind of like in a calculus course or an algebra class, how thick is a line? Well, it's infinitely thin. There's infinitesimally thin. There's no real thickness to it. It represents an imaginary surface. Now, we could define the boundary with some real surface. Like if I say my body is my system that I want to analyze, then I could say my skin could serve as the boundary. And what I could do is I could represent that skin with a very, very thin dotted line right at the surface of my skin, and that could represent the actual boundary. So anyway, again, a boundary can be a real surface, or it can be just we just say, well, here's a box of air. I'm just going to draw a dotted line around this box of air in front of my face, and that becomes my system. That's all perfectly fine. Okay. There are two types of systems, right? Two types of systems. One is a closed system, right? So closed is closed to mass flow. There's no mass crossing the boundary. A closed system is a fixed amount of mass. And then as opposed to, say, a control volume, where you can have mass flowing in or out. But if we go back and we look at a closed system here, so again, we're saying that there's no mass crossing the boundary, but energy can cross the boundary, right? Now, what we have here is this is a diagram of what we would call it's an S, very poorly drawn S, but it's an S all the same. This is a piston cylinder. And a piston cylinder is a classic closed system where the volume can change. This lid right here, right? This lid right here, that can move up and down. And if I've got a good tight seal right here at the walls of my system, right? A good tight seal right here and right here, and this thing moves up and down, well, that means the volume of my system can change in a piston cylinder, but the mass cannot, right? So the volume can change. Can change. This is a classic closed system where the volume can change as a piston cylinder, as opposed to, say, a control volume. So a control volume is, again, poorly defined, very vaguely defined as a properly selected region in space. And that's, again, sufficiently vague to be useless. Um, a control volume is simply this. It's a system where mass can flow into and or out of the system. So mass can cross the system boundary. For example, this is like a refrigeration tower or cooling tower on a central air conditioner system unit. Um, I'm teaching this class right now in the summer, so you probably have some kind of air conditioning going possibly. Um, and so this is an example. The way this works is if you were to walk up to this thing while it's running, you would feel air coming out of this, and it would be hot air. And what's actually happening is that fan is pulling more air into this thing in all directions, right? So it's pulling air in and it's pushing hotter air out. So it's basically warming up the air that's flowing through it. And what it's actually doing then, so it's doing a couple of things. This has mass flowing in multiple places. So another thing it's got going on here is it's got refrigerant. So see this insulated pipe, this thicker looking pipe, that's sending cool refrigerant back into the house, and warmer refrigerant is flowing into this other pipe right here, this one that's not insulated, a little thinner looking pipe. We're pushing refrigerant into and out of the air conditioned space. Right? So I've got mass in the form of a refrigerant coming into this cooling unit. It's going through a process where it's changing phase and state, and it gets sent back after being compressed and then basically cooled off by the air and then sent back into the house at a lower temperature. So essentially what's happening is we've got energy coming in right here from the refrigerant at a higher temperature, a process occurs where basically its temperature gets jacked up, and then the air is used to cool that refrigerant down, remove some energy. So energy is going out here from the air going out, and then we can send back lower energy refrigerant back into the house to cool the house down. We're going to learn more about this in chapter 6. I don't know, probably lecture 18 or so. So if you want to skip ahead and learn more about how refrigerators, and air conditioning systems work, there's a much more in-depth explanation there. For right now, notice where I've drawn my system boundary. The black dotted line there represents my boundary, and I've got mass coming into and out of the system. Perfect example of a control volume, something where mass crosses the boundary. So again, if I go back, closed system, no mass crossing the boundary. Control volume, mass flows into and or out of the system. So mass flow in a control volume, no mass flow in a closed system. Two types of systems. What is a system? If you don't know a system, pause it and look it up in your notes. And if you don't have notes, shame on you. Seriously, pause here if you don't know what a system is and come back. Okay, you good? All right, let's keep going, shall we? Okay, looking at my time here, I'm trying to keep these reasonable amount of time on these. Other things to talk about. Property. So property is something that we would measure for our system. It's a characteristic of our system. Three properties that we would want to measure would be temperature, pressure, and volume. Um, Now, there are two categories of properties, and this one we're going to mention here and there, but it's probably not something I would test you directly on, but it's good to know. The idea of an intensive versus an extensive property. So an intensive property is independent of the mass of the system, the extent of the system. It's independent of the extent of the system. Whereas an extensive property is dependent on how big the system is, how much mass is present. What is the extent of the system? Because the perfect prop is always my water cup here. So I've got a certain amount of water here, and you can, I don't know, I'm not going to pour water on my keyboard, but there's a certain amount of water in this cup here. And so it has a volume. There's a volume of water in my cup. Okay. And that's my timer here. We're going to go just a little bit longer on this. There's a volume of water in my cup. Now, if I were to change the mass of the water, let's say the water is my system, and I change the mass of the water, right? Now I've changed the mass of my water. Notice the volume has changed. The volume is what we call an extensive property. But what about something like, say, the density of this water? Has that changed? Oh, actually, it hasn't. The density of your system is an example of an intensive property. Doesn't matter how much mass is there. Temperature, pressure, density. We're going to talk about several other intensive properties throughout the semester. But the density of the water, as long as it's in a liquid form, in my cup is the same in that cup as it would be in essentially an Olympic-sized swimming pool. The density is not going to change based on the amount of mass present. The total volume will. More mass, the more volume. Um, what will change the density would be like the temperature. If we heated the water up, it will increase in volume and the same amount of mass, therefore its density will change. So the density is dependent on things that are not the mass, where volume is going to be dependent on the mass. That's intensive, not dependent on the extent of the system. Extensive is dependent on the mass or the extent of the system. Okay? All right, I'm going to stop there and we'll pick up the next video.